Alrighty, so there's a couple of definitions and terms that I want to go over. The first one is, what does it mean for an electron configuration to be in the ground state? And a lot of textbooks or practice problems will tell you, write the ground state electron configuration for carbon. This is what you've been doing all along. It doesn't change anything about the process. What they're referring to is the fact that the Aufbau principle is followed. Sometimes the electrons, and I'll draw the Bohr model here, even though it's not the most accurate model. So you have your nucleus in the center, and you have your first shell, so I'll do n equals 1, and then you have your second shell. Sometimes what happens is some kind of energy comes in and hits that electron. And even though that electron is normally in the first shell, and that's where it's most stable, because of that incoming energy, the electron gets excited and jumps to the second shell. And that's just temporary. That's known as an excited electron. These jumps are hard to predict. We're not going to capture them in an electron configuration. The ground state electron configuration is the most stable configuration, the one that's easiest to predict. It's because we filled out all those lower energy orbitals. We put the electrons in the most stable orbitals before using higher energy ones. An excited electron is very unstable. And again, it occurs when some incoming energy hits the electron and causes it to jump to a higher energy orbital. So the electron is in a higher energy orbital. Eventually, it's gonna fall down and return to its original orbital. When it does that, it actually emits light. And this is the light that we see in fireworks and, when you're in the lab and you burn sodium and it looks orange. And that's because the fire is causing the electrons to jump up, and then the orange light is emitted as the electrons return to their ground state. So I have a question for you. Hamburger or steak? Which one's lower in energy? It's more like a riddle, right? Very nerdy chemistry riddle. So it's going to be hamburger because it's in the ground state. And then all of you are supposed to moan or say boo. It's in the ground state. I left out the word the. Anyways, the ground state is lower in energy. Two more definitions. Valence electrons are the outer electrons. And you know that. We've been doing Lewis dot structures. You know how to get the number of valence electrons off of your periodic table. Why this is important right now is you need to be able to identify the valence electrons in an electron configuration so that you can write the electron configuration of an ion. So in terms of the electron configuration, the valence electrons have the highest shell number. So for instance, let me write an electron configuration real quick. Titanium, number 22. We're going to have argon, 4s2, 3d2. So even though 3d was the last subshell that I started filling, because 4 is higher than 3, this is going to be the valence or the valence electrons of the titanium element. Core electrons are those inner electrons. We usually don't mess with them. They're unavailable for reactions. They're difficult to disturb. they're very stable. In the electron configurations, you designate your core electrons by your noble gas. And that's why we can do that, because we don't really care. Nothing's going to happen to those electrons that have such lower energies compared to the last electrons that you threw in there. In question 7, we're asked to name elements in the 4th row of the periodic table. In 7a, they specifically tell us that the element has 5 valence electrons. So the issue here is that the valence electron should have the highest shell number. And when we're in the 4th row, we have 4s1, 4s2, but then by the time we get to an atomic number of 21, we're at the D block. Remember, the D block lags 1 behind. So this is 3D, and I wouldn't count this as a valence electron. So all of these D's in here are not going to be part of the valence. So I have 1 valence electron, 2 valence electrons, and then by the time I get back to the P block, I'm at a principal quantum number of 4 again. So 4s1, 4s2, skip all the D's because they're down a number, and then now I have 4p1, 4p2, 4p3. So I would go with arsenic as my answer to A. And just to complete that, let's write the electron configuration for the arsenic. So we're going to have argon, 4s2, because we're in the 4th row. I am going to write 3d10, even though it doesn't count towards my valence. And then 4p1, 4p2, 4p3. So looking back at this, these are my valence electrons, the 4s2 and the 4p3. (4b) has us identifying an element with 4 4p electrons. So 4p1, 4p2, 4p3, 4p4. So that looks like it's going to be selenium. And again, I'm going to write the electron configuration here just to verify my answer. So we're going to do argon, 4s2, 3d10, four p1, 4p2, 4p3, 4p4. Letter C says, find an element with 3 3d electrons. So once we pass 4s2, then we're at the 3d block. So this would be 1 d electron, 2 d electrons, and then this would be the 3rd d electron. So we're looking at vanadium, and I'm just going to write the electron configuration. So it's going to be 4s2, 3d3. The last one says we need an electron with a complete outer shell. And those are our noble gases. And the fact that it has a complete outer shell explains why our noble gases are typically unreactive. So we're looking at Krypton here. And its electron configuration is going to be 4s2, 3d10, and then 4p1, 4p2, 4p3, 4p4, 4p5, 4p6. And when we went over the Lewis dot structures, there was a lot of emphasis on having 8 valence electrons, having that complete octet. Hopefully now, like, some of the pieces are starting to come together. And we have the 4s2 and the 4ps, which are our valence electrons here. And if we add them up, we get 2 plus 6. So altogether, with our noble gases, we'll have 8 valence electrons. Alrighty, in this next example here, we're asked to figure out the electron configuration of vanadium 2+. When you start writing the electron configurations of ions, I can't emphasize this enough. Make sure you write the electron configuration of the neutral species first. So I'm going to write the electron configuration for neutral vanadium. And actually, this is one we just did in the previous problem. So it's argon 4s2 3d3. That's vanadium before it lost any electrons. The 2+ tells us it's going to lose 2 electrons. When elements lose electrons, they lose electrons from their valence shell. And by definition, the valence shell of, or the valence subshell of vanadium is going to be 4s2. How do we know these are the valence electrons? Well, it's just based off of the shell number. So since 4 is greater than 3, we're going to take electrons out of the 4th subshell before we start messing with the 3rd subshell, or 3rd shell. Alrighty, so since we found the valence electrons, then we can say that vanadium 2+, both of these are going to go away, or be lost, and then we're left with argon 3d3. Continuing on with more electron configurations of ions. So we got chloride ion. So chlorine as a neutral element has 17 electrons. So I looked at the atomic number, right? It's number 17. But the negative tells me it gained 1. So chloride is going to have 18 electrons. And so just like we were filling out those energy diagrams before, this is going to look super similar. I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And now we're starting to see why chloride wants to gain just 1 electron. That enabled it to fill up its 3rd shell completely. It doesn't have any empty space, and that makes it super stable. So in terms of writing the electron configuration of chloride, write the full one since I filled out the energy diagram. I'm going to do 1s2, 2s2, 2p6, 3s2, and 3p6. Next one is cadmium 2+. Still going to approach it the same way. I'm going to try to do neutral cadmium. So that's going to have 48 electrons in its neutral form. So I'll do, let me grab my orange. So I'll do 1, 2, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. So that's all 48 electrons of neutral cadmium. Which electrons are part of that valence shell or valence subshell? Which electrons are valence electrons? So looking at all of the subshells that we used, the highest row number or highest shell number that I see is 5. So right there we got a 5s. Because 5 is higher than everything else on here that we used, we're not going to count the ones we didn't use, but 5 is higher than the 4s and the 3s. That means that the 5s is our valence shell. This right here is going to be our valence electrons. Remember, electrons should always come out of the valence shell. So when we do cadmium 2+, even though the 5s is a little bit lower in energy, we would remove the electrons from that subshell. And I'm removing 2 because it's a 2 plus. At the end of the day, that leaves us with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. I'm moving on underneath. I ran out of room. 3d10, 4p6. I'm skipping the 5s2. Those are the ones that got lost. 4d10. Alright, 9a has us writing the electron configuration for bromide. So it's really important to be careful when you have cations, when you have positively charged ions. When you have an anion, something with a negative charge, it's not as tricky. You just kind of just throw that extra electron on there. So bromine is number 35 on the periodic table. And when I have Br minus, it's going to look like krypton. It's going to be isoelectronic with krypton. And so sometimes I actually even have students that'll tell me Br minus, well, the electron configuration is simply Kr. And honestly, I have to take it because they're not wrong. Bromine, by gaining that extra electron and becoming bromide, now looks, in terms of its electrons, just like krypton. I could also go back and write it starting at argon. And then that leaves me in the 4th row. So I'll do 4s2, and then 3d. This is our 3d block. We're going to use all of it. So we'll do a 3d10, 4p1, 4p2, 4p3, 4p4, 4p5, 4p6. Next, we're asked to write the electron configuration of copper 2 plus. Now, because this is a cation, I need to take my time. So copper's right there. Ooh, another thing we need to discuss about copper, and this is the last page of this lecture packet. Copper is what's known as an anomaly. So it takes one of its 4s electrons and promotes it to the 3d block so that it can fill up its d subshell. And again, I go into more detail about that on the last page of this lecture packet. So neutral copper, we're going to use argon. And then we're in the 4th row. And normally we would do 4s2, but copper's weird and does 4s1. And then it takes that extra electron and uses it to fill up the D block. So after that, it'll do 3d10. Who are the valence electrons in copper? 4s1 is definitely part of that valence shell. And we do see copper doing a +1 charge quite often. So copper +1 would be argon 3d10. But for copper 2 plus, well, what are we going to do? We already took it away from the 4s, so we do have to start kind of disturbing the full D subshell. So we're going to do a 3d9 after that. Last example here is selenium. It's a selenium 2 minus. So that means selenium gained 2 electrons, and it's going to look like krypton. So again, kind of like in our previous example with the bromide, we can write this like this, or we can start at argon in the previous row and just fill out that next row. Totally up to you, whatever version you prefer, whatever sits better and makes more sense to you. All right, let's look at potassium then. As a neutral species, I would do argon 4s1. So when it's potassium plus 1, it's going to be isoelectronic with argon. So iso means the same, and electrons, right? Same number of electrons. So these two things have the same electron configuration. For iron 3 plus, for the neutral iron, it's argon, 4s2, 3d6. So here's an interesting example. We see that the valence is the 4s2. And that's going to drop out as we're trying to obtain a +3 charge. After that, we don't have a choice but to take another electron from the 3d. And so the 3d would go down to a 3d5. So you might be wondering, why does that happen? I mean, we've seen a +2 with iron, and the +2 is easy to justify, right? We just are taking away the valence shell. But why does it do a 3d5 or a +3? And that's because there's increased stability associated with half-filled subshells. So I'll do something like this. Argon, and then we have our 3d, and then 1, 2, 3, 4, 5. So this would be for iron 3 plus. And once again, there's a greater level of stability associated with half-filled subshells. You're minimizing electron-electron repulsion. So if we kept it at 3d6, right, then those two negative charges are in the same orbital. They're fighting for the same space. So it makes sense that a +3 can happen. Everything that you see happen in chemistry is motivated by an increase in stability or an increase in entropy. I shouldn't just say that, but all right, hafnium. As a neutral species, we have xenon. We're in the 6th row, so we're going to do 6s2. We're going to fill up the whole F block, 4f14, and then I come back up and I need 2 electrons that I need to put into the 5d block. So that's as a neutral species. So valence is going to be our 6s, but we need to lose 4. So we're going to lose from 6. Next, we're going to lose from 5, because 5 is higher than 4. What else is happening, though, to emphasize this increase in stability, as a cation, the hafnium is left with a full subshell. And that also is a very stable place to be. You can look it up. There's a bunch of different ions that are transition metals can form, and maybe hafnium 2+ is a possibility. But if you have a 2+, then you still have this 5d2 hanging about, and it's just kind of messy, and unstable. Not completely unstable, but it's more stable to get rid of it and have a full subshell. Last one, nickel. We got argon, 4s2, 3d8 as our neutral electron configuration. Our valence is the 4s2. So my nickel 2+ is going to have an electron configuration of argon, 3d8. Typically, I ask students to know 5 different anomalies, which are just exceptions to the order of filling that we would expect with our electron configurations. So there's 5 in the main part of the periodic table, and then there's something like 20+ exceptions if you include all the exceptions that we see in the F block, in the inner transition metals. But I try not to go there too much because that's overwhelming, and again, it's not that predictable. However, the 5 I like students to know are predictable if we start thinking about why do these exceptions occur. So I had you all write what you would think would be the electron configuration of silver. So I imagine most of you wrote 5s249. Let's do a little energy diagram for the valence electrons of silver. So Krypton, nothing interesting going on with the core, right? And then we have 5s2. And if you take a look at your energy diagram, the energy difference between 5s and 4d is not that significant, right? So we have a very small energy difference. I'm going to put my 2 electrons here, and then my 9 electrons in the 4d. So what's happening here, and why is silver an anomaly? Well, there's so much stability to be gained if you have a full subshell. And there's such a small energy difference. And the 4d is only 1 electron away from having a full subshell. So this electron that we would think would be in the 5s actually moves over to the 4d. And that creates this full subshell. Our core is full. And then we just have a random electron hanging out in the 5s1. So let me cross this one out because this one's wrong. Silver, the correct electron configuration will be Krypton, 5s1, 4d10. And the fact that you had to memorize, 99.9% of the time, silver does a +1 charge. Why? Well, we see that now because its valence only has 1 electron, and getting rid of that would mean that all the subshells, all the shells after that are nice and full and stable. So besides silver, everyone in that same group there will exhibit a similar anomaly. So we see the same anomaly with copper and gold as well, where you're going to have NS1 and -1 D10 as your electron configuration. For chromium, I imagine you all wrote down this. Let's do the same kind of analysis. We have argon, and then our 4s, and then very close in energy, our 3d. The fact that the energy differences are so small as we get to the higher parts of the energy diagram are critical to this being able to occur. You're not ever going to promote an electron from like a 1s to a 2s just because, right? Maybe if there's energy coming in, it might happen, but it's not just going to be rearranged on its own. So we see that there's 2 electrons in the same orbital, and then there's a whole bunch of singles, and then there's an empty orbital. So it's almost like the 4s and the 3d are a single subshell, and we just fill singly going across. So we have all singles. And we've minimized electron-electron repulsion by doing that, by giving everybody their own space. It's almost like the most extreme example of Hund's rule, right? And the energy difference is so small that we're thinking of it almost as a degenerate set of orbitals. So this is wrong. And we're going to do argon, 4s1, 3d10. apart from chromium. We also see this with molybdenum. And I can kind of generalize it to say we're going to have NS1 and -1 D5 as our generalized electron configuration. So the noble gas that I'm going to use is Krypton. And then we're on the fifth row. So we're going to have 5s and 4d. And then after that, 5p, but we don't even need that. So if we were just filling them out and following the Aufbau principle 110%, I would do 5s2, 4d4. But because there's increased stability with that half-filled subshell, one of these 4s electrons gets promoted over to the 4d subshell. So at the end of the day, we're going to have argon 5s1, 4d5. Next, we're asked to write the noble gas electron configuration for the silver +1 ion. I love this problem so much because in the beginning of the course, I ask everyone to memorize the fact that silver likes to do a +1. And now we can explain why. So silver on our periodic table is in the fifth row. So I'm going to use Krypton as my noble gas. And so I'll do 5s and 4d, 1, 2, 3, 4, 5. And then after that, we're going to have 5p. Silver, if we didn't know better, we'd do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we think it looks something like that. That it's pretty close to filling out its D subshell, but not quite there. And what I'm drawing right now is for neutral silver. So first things first, the element is really motivated to increase its stability by filling out that 4d subshell. So it's going to take this electron and move it over here, promote it to that subshell, and then it gains a full subshell. However, it's silver +1. So the 5s is the valence. And even though there's only one electron in there, that's going to be the electron that's lost when it obtains the +1 configuration. So silver +1 is going to be Krypton. 5s is gone. It lost the 1 from there. 4d10.